Hi, I'm an old guy and I do maths, and today we're looking in very general terms at a thing called a general solution, and I'm going to try and explain what the general solution of a trig function actually means. So, I have drawn here a very rough sketch of a sine graph that just rolls on, y equals sine of x. And it doesn't have a restriction on the domain by the look of it, because it will run on positively and negatively off the page. And let us say that we have such a situation where we just have an unrestricted domain and we want to know where on that graph a certain value will occur. Well, I've picked this value here. It's a positive value, but we don't need to say anything beyond that. And the graph touches that value here, 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 and here, and here. And it does so continuously. And there are predictable gaps between here and here, and here and here. And what a general solution sets out to do is it sets out to describe those gaps and a starting point. So let's try an example. And I don't mean to sow confusion by what I'm about to do, but I'm going to use a tangent function to do this. I'm not going to draw the tangent function. I'm going to use the unit circle to describe what's going on. And from that, I will derive the general solution to the following. The general solution for that. Now, if we look at this little triangle here, this should be familiar to many of you. We have 1, 1, root 2. It's an isosceles triangle, right angle triangle. This angle in here is 45 degrees, pi on 4. And the tangent of pi on 4 is 1 over 1, which is 1. So we know that the tangent of pi on 4, or 45 degrees, is equal to 1. Right, well that's fine. But if we were to have an unrestricted domain, say for the asymptotes on a tangent graph, what we would discover is that if we drew in our values, and we'll use the unit circle to do this on because it's more efficient, we have this angle here of 45 degrees, pi on 4, and down here we have a corresponding angle from the x-axis of 45 degrees, pi on 4, and the tangent of this angle is also 1. Because all the signs are positive here, sines are positive here, tangents are positive here, and cosines are positive here, which means that if we drew the tangent angle in here, it would be -1, and if we did the same here, it would be -1. But here, it has a value of 1, 1 over 1, and here it has a value of 1. Now, imagine that, just like up here, our tangent graph did not have a restricted domain. How would we describe when and where the tangent of x was equal to 1? Well, we can start with pi on 4. But what happens if we move around here, the equivalent of 1 pi, 180 degrees? We hit it again. What happens if we move around to here, 180 degrees? We hit it again, and again, and again, and again, unless our domain is somehow restricted. So, what do we wind up with? Well, we wind up with plus pi. And it doesn't matter how many times we add pi to this, we will always wind up, if we start here, we will always wind up here. Once we get to here, we'll wind up here, and so forth and so on. And so we don't know how many times we're going to go around here, so we will name the number of times that we add pi to this as simply n. It could be 5 times. 1, 2, 3, 4, 5. That's it in really simple terms. Now, here's a little bit more. What happens if we go this way? Well, the same thing happens. So pi n. We can go in reverse. And so we could normally write this as pi on 4 plus or minus pi n. Or pi n, best this way. Pi on 4 plus or minus pi n. That, very, very briefly, is the general solution in this case. Now, this will be followed up with specific examples of general solutions. More often than not, you'll be asked to do them for sines and cosines when you're in high school. I chose a tangent because it was a simple example to do. And as I say, we will come to more difficult examples in the playlist. So I hope this was helpful. Thank you very much for watching. And if you did find it useful, please like and subscribe, and I'll see you next time. Bye-bye.